Let's dive right into this explainer and completely demystify how we can command heavy-duty hardware using some seriously simple inputs. Today, we're unpacking a highly effective schematic designed to give you total, precise control over high-power physical movement.
It's a classic engineering dilemma, right? Every robotics enthusiast, maker, or engineer faces this exact problem when bridging the gap between low-voltage logic and raw power. You want to make something move with a simple button press, but if you hook up a massive 24-volt motor directly to your delicate switches or microcontrollers, you're looking at an instant meltdown. And that's exactly what this brilliantly illustrates. It's a complete, incredibly elegant circuit design by Technomaster that safely routes 12-volt or 24-volt DC power right to our motor. By taking a look at this full schematic, we can see exactly how to achieve smooth bidirectional control without putting a single one of those delicate control inputs at risk.
To make sense of all this, here is our roadmap. First, we'll meet the hardware. Second, we look at the L298 motor driver. Third, wiring forward and reverse. And finally, power, protection, and transistors. We're going to follow this signal journey step by step, so you can confidently build this the next time you're at the workbench.
Starting with Part 1, Meet the Hardware, the components of control. Let's take a quick inventory of the players on our board.
Beyond the primary high-power DC motor and our 12 or 24-volt power source, this setup relies on some highly specific modules. We've got the L298 driver sitting right in the middle, a BC547 transistor over on the left, distinct forward and reverse push buttons at the bottom, and a handful of vital passive components, specifically some 10-ohm resistors and 0.1 microfarad capacitors.
Moving on to Part 2, the L298N Motor Driver. The real heavy lifter here. Honestly, this is the true brain of our whole operation. The absolutely crucial point here is that this module handles the heavy current that would literally destroy a standard microcontroller or a basic switch. Think of the L298N as your central traffic cop, or a robust barrier. It takes those tiny, safe signals from your buttons and translates them into massive high-current actions that actually drive the motor.
Notice how centrally located the L298N is in the schematic. It's acting as the main junction box between those lower inputs and the high-powered DC motor over on the right. You can clearly spot its large black heatsink at the top, which, by the way, is essential for dissipating all the heat generated by those heavy currents. Down at the bottom, we have our ENA and IN2 logic terminals, and on the right side, the out terminals are securely wired directly to the motor.
That brings us to Part 3, wiring forward and reverse, or directing the flow. So how exactly do we translate a simple button press into a specific physical direction?
Well, by isolating the left and right button presses into distinct red and blue signal paths, we achieve really clear bidirectional control. The red wiring handles the forward command, routing the signal right to the ENA side of the driver. Meanwhile, the blue wiring handles reverse, routing its signal entirely independently over to the IN2 side.
Visually tracing these paths reveals exactly how all this magic happens. Just follow that red wire from the forward button on the left. It goes straight up, passes right through a 10-ohm resistor, and connects securely into the module's left terminal. Meanwhile, the blue path coming from the reverse button weaves its way over to the IN2 terminal. It's basically a perfect visual map of how isolated signals trigger totally different internal switches inside the L298.
Putting it all together gives us this incredibly clean, reliable sequence. The moment your 12V or 24V DC power is applied, boom, the system is armed. The user presses either the forward or reverse button, sending an electrical signal routing cleanly through those distinct paths to specific L290N pins. And almost instantly, the motor spins in the chosen direction. This strict logical cause and effect is what ensures every single press safely translates into motion.
And finally, Part 4, power, protection, and transistors, essentially keeping the whole thing safe. We really need to address the unsung heroes of this schematic, because, it's not just about making the motor turn, it's about making absolutely sure it doesn't break everything else in the process. Take a look over on the left side, featuring the BC547 transistor, and definitely don't miss those 10-ohm resistors on the control lines. But even more importantly, spot that 0.1 microfarad capacitor bridging the logic lines right under the driver, and then another capacitor soldered directly across the motor's terminals on the right.
These might seem like minor additions, but they are absolutely critical. See, large DC motors act like really messy generators when they start and stop, just throwing out crazy voltage spikes and electrical noise. These capacitors and the BC547 transistor step in as vital stabilizers. They dampen those dangerous spikes, acting like electrical shock absorbers, so our central traffic cop doesn't get confused or overwhelmed by dirty signals. Guys, this is literally the difference between a project that works once and a project that works reliably forever.
So now that you understand the complete signal journey from the main power supply straight through the isolated buttons into the protected L298 driver and finally out to the spinning motor, your foundation is totally set. Whether you're building an automated rover, a heavy-duty conveyor belt, or some custom robotics, you now have the exact blueprint to command it safely. The only question left is, what heavy-duty project are you going to bring to life next?